So this is part 2. In the last video we had talked about evaluating the moment of inertia of this rather odd parabola shape, and we found a nice lengthy expression that shouldn't be too complicated to do. We know what h and b are, we know what m is, and we simply just need to do an integral of a polynomial. And so that could be rather nice. But one shortcut I might suggest doing is that since this happens to be symmetric, the integral, we're integrating over x across this thing, and because it's symmetric about the x-axis, what we could do is instead of evaluating from the limits of negative square root of h over b to the positive square root of h over b, what we could do is evaluate from 0 to square root of h over b and then simply multiply the integral by 2. It's a trick that you guys probably saw in your class from time to time, and something that physics people really like to do a lot because it makes the work a little bit easier. And so I would strongly consider doing that. If I were to evaluate this again, I would probably do that. The last thing that we don't know anything about, though, is the area. Right? We don't exactly know what the area is, but we've basically done all of the legwork to do it, whether we realize it or not. What we need to do, the area, is simply the length of all these strips. Now, we talked about these strips before because we were looking for the differential area to plug into this our expression for the moment of inertia. We needed to find what the differential area was so we could relate the differential mass to the surface area density. So that's really all we're trying to do, is just recreate what this dA is. And if you look right here in this step, right, what is dA? dA is equal to is h minus bx squared times dx. That's exactly what dA was. And so if we can integrate, let's just write that down real quick, right? Let's dA is equal to h minus bx squared dx. So if we integrate both sides, the left side, we can figure out what the area is, the integral of this expression, and I'm going to do that trick that I mentioned at the beginning. Instead of doing it, the limit from negative square root of h over b to positive square root of h over b, we're going to go from 0 to square root of h over b and then multiply our integrand by 2. That's times the integral of h minus bx squared dx. So that's the integral that we're going to perform to get this expression. And just to sketch that out real quick in case you don't want to go back to the previous video, the way that we got that was by identifying these strips, right? What we want to do is that if we had, you can think about the sum of all these strips here. If we can count up a whole bunch of different strips and figure out what the areas of each of these strips are and then sum up over those strips, well, that would be great. And that's what we do, but except we get slits that are very, very, have a very, very small width. So as this width of x, this little dimension of x, gets very, very small, and that becomes dx, then we need to know what the height of that strip is, and that height happens to always be equal to h minus bx squared. And so that's what this length is equal to, that value of y at any point x. So as we sum up all of these pieces, that's what we're going to do. So we sum them up very quickly because we have infinitesimally small pieces, and the way we do that is through this integral. So you can evaluate this integral, and you'll get some number for the area of this object, and then we're going to evaluate this integral for the moment of inertia, plugging in that number for a. All right? And hopefully you'll have success. Again, this is a challenging problem to set up. One of the reasons why we don't spend a lot of time doing it in class, why we don't spend a lot of time asking questions about this for the exam. But hopefully some of this made sense, and if you have any questions, I'll be happy to answer them. Good luck.